Now just let us look at this example again. Omega naught and omega means the initial angular velocity, omega naught, and final angular velocity was given to us, and 16 seconds was the time taken to reach the angular velocity from 1200 rpm to 3120 rpm. So we have changed these angular velocities to their SI units. So 1200 revolution per minute. So one revolution means the angle is 2 pi radians. So we have changed one revolution with 2 pi radian and 1 minute with 60 seconds, and we get omega naught as 40 pi and we get omega as 104 pi, and then we have found the value of angular acceleration. So first part we have done. Now the second part, number of revolution. Number of revolution means we have to find the angular displacement. So we can use any of these two formulas. So let us use this one. So theta equals to omega naught is this is your omega naught, 40 pi radians per second into time, that is your 16 seconds, plus half into what's your alpha, that is 4 pi radian per second square, into what is your time, 16 seconds, so 16 square. And the students, the unit of this angular displacement is radians, right? So we simplify it and ultimately we get here 1152 pi radians. Okay, so now we know that 2 pi radian is equals to 1 revolution, so we have to find the answer in revolutions. So simply this radians will go back to the revolution if we divide it with 2 pi. Okay, and this comes out to be 576 revolutions. So that's example 7.14. Any problems, students?
No, sir.
No, sir.
Okay. Now let us do the next topic, which is 7.12. Dynamics of rotational motion. So in kinematics we study the equations of motion, and in dynamics we study what causes motion. So what causes motion? What causes rotational motion? So it is the torque that causes rotational motion. So like we did earlier, we have to write the equations for linear motion and then for rotational motion. And always remember that here acceleration is constant in all the equations. And remember here that your axis is fixed. Okay, so what are the variables here? Like see, we have the table 7.2 in our NCERT book. So students, open your NCERT books, page number 170. Okay, I hope all of you have opened.
Yes, sir.
So students, just look at these 9 formulas. So here we derived the 3 equations of motions. Yesterday we did it, and now these are the formulas, so you can clearly see displacement x, angular displacement. So word angular is added. Velocity dx by dt, angular velocity d theta by dt. Acceleration dv by dt, acceleration d. So simply you are replacing what you are doing. Simply you are replacing like x with theta, v with omega, a with alpha, and like if you have u and v both, so then you are replacing v with omega naught, u with omega naught, and v with omega, right? And then you are replacing mass with moment of inertia. Student, this is the most important thing here. Why I am calling it most important? Moment of inertia. See, because here in the mass, simply it was given to you in the questions. Almost all the questions you were given the mass 2 kg. So you need not to do anything. You just need to directly put the value that this is mass 2 kg, done. But here in moment of inertia, you need to use table number, and you need to remember these formulas. Okay, this table will not be given to you. Okay, so table 7.1. So these values you will find from table 7.1. So see table 7. So we will see 7.1 table also today. Let us finish these formulas. So this moment of inertia, it is different for different objects, and even if a particular object is rotating about different axis, still it will be moment of inertia will be different. And moment of inertia plays the same role as the mass plays. Mass doesn't allow the body to change its state of linear motion. So moment of inertia also doesn't allow the body to change its rotational state of motion. If it is rotating, moment of inertia want it to keep on rotating. If it is at rest, it doesn't want it to rotate. Okay, now the next, force is equals to mass into acceleration. So instead of mass, we are replacing it with moment of inertia, and this we need to calculate. Not calculate, we have already calculated the formulas, so but we need to apply the formulas and calculate the value of I. Yes, so we need to use the formula here. Okay, so there was no formula for mass here, but there is formula for moment of inertia, and we have to use the formulas using table 7.1. Now force is equals to mass into acceleration, and here we have moment of force, that is torque. So torque is equals to I alpha. So students, we have two formula of torque. One is tau is equals to R cross F, you know it, that is equals to, so in terms of magnitude we write tau is equals to R perpendicular into F. So we have two formulas, tau is equals to I alpha and tau is equals to R perpendicular into F. Now we have small work done here. So work done is equals to so F dot ds. So we have written small work done because suppose if this is varying, this force, so then for small displacement it will be treated as constant. Now for work here in case of rotational motion, force will be replaced with tau and ds will be replaced with d theta. And kinetic energy, half mv square. So here instead of so half mv square, half mass is replaced with I and v is replaced with angular velocity. Power, we know the power is equals to F into V, and here power is equals to omega means force is represented by torque and V with. So we know the formula of power. So this instantaneous power, you can see the instantaneous power is equals to dw by dt, rate of change of work done, and work done is F into S. So here means force is constant and ds by dt, and ds by dt is velocity, so that is F into V. So that's the formula. Okay, so power, these are the formulas of power. So work done upon time taken, and now new formula we have derived in 11th class, that is force into velocity. So here also power is equals to d, so here it was dw by dt, here also it is dw by dt, and that's equals to force is your torque here, so d by dt, if you want to put the value, that is tau into angular displacement is suppose theta, and tau is constant, will come outside, and this is d theta by dt, and d theta by dt is your angular velocity. So power is equals to this tau omega. Now we have linear momentum, that is mass into velocity, and here we have angular momentum, that is instead of mass I have moment of inertia into angular velocity. Now let us try to so I hope you have learned these formulas, right, and how to learn them, you know how to write these formulas. Now let us look at table 7.1, how to remember table 7.1. Veena, is there any queries?
No, sir.
Mansi, Harsh,
No, sir. No query.
okay, Bhumika, Karthik, Sakshi,
No, sir. No, sir.
okay, Vinay, Piyush, any queries?
No, sir.
Okay. So students, I hope you have started enjoying this chapter. You have spent so much of time on it. Okay. Now, so we have this ring over here. In first two formulas are about the ring. This one is about rod. These two are about the disc, and these two are about the cylinders, and this is about sphere. Okay, we have, of course, we have moment of inertia of each and every body, but right now we are dealing with only these 5 solid figures. Okay, all of them are regular figures, right? So so in case of ring, if we are rotating the ring, so here the body means one variable is given to you, that is radius here, that is capital R, radius capital R, length is L, circular radius capital R. So there is nothing to be remember here in this column. Now what about the axis? See here, this is the axis of rotation. So it is perpendicular to the plane of the ring at the center. It is along the diameter, so it is rotating along the diameter. It is perpendicular to the midpoint of the rod. So this is along the z-axis, the rotation you can see. And now this is perpendicular to the disk at the center, same as this case, and same here this case. Now in case of cylinder, it is along the axis of the cylinder. So student, it doesn't matter whether you are means like this or it is vertically, so that's the same thing. So point is that it is along the axis of the cylinder. So the difference is here we have a hollow cylinder, this one is hollow and this one is solid. So and here we have the axis is along the diameter in the solid sphere. So this is solid sphere. So how to remember these formulas? So this formula is mr square. Okay, the ring in this rotation. And now let us see for the disk. So in the disk we have filled this filled the material inside, and here the formula is mr square by 2. So here if we have filled it because you know that inertia depends on the I is equals to mr square, so it depends on the mass plus the means this. If I have only one material here, means if I have taken only one particle P which is rotating, this particle P belongs to extended body, of course, so this particle has mass m, so the moment of inertia of this particle will be m, and this is its distance from the axis of rotation, so that is mr square. So moment of inertia depends on how your mass is distributed along the axis of rotation. So more near the mass will be to the axis of rotation, so lesser the distance, lesser will be the inertia. So it is easy to rotate the body. So here it is easy to rotate because the mass is reached near to the axis of rotation. That is why it is decreased by half. Got it, students? Now if we means rotate it along with the diameter, you can see that still we are near. Now the mass, see there is no mass up to distance r, but here with the axis of rotation this mass is reached near to the, so that is why here also along the diameter also it is reduced by half. So first thing, it is reduced by half when we have taken from this hollow ring means ring to the disk, and the second thing is that if we take the axis along diameter, again it is reduced by half. So if we take this disk by diameter, again it will be reduced by half. So this is half already, so it will become 1/4. Okay?
Not okay, sir. समझ में नहीं आया.
But see, the thing is that you need to derive these formulas. Okay, you need to remember these formulas. I am just telling you a simple way to remember, how to remember them. I am not deriving them here. Okay, I am not deriving them here. I am just trying to find a way how to remember these formulas. These formulas, from where I have done the derivation. In the previous lecture, means last to last lecture, I have derived these formulas, mr square by 2. I have derived these formulas, these two formulas, and I have told you. And these formula, the derivation is given in SL Aroda book. Okay. Here I am simply telling you how to remember these formulas. Very simple way I have told you is that if it is perpendicular to the plane of the center, then it is mr square. Okay. So here in case of disk, as this is filled, so if it is filled, the moment of inertia will be lesser. So moment of inertia, which was over here mr square, I have simply divided with 2. Okay. In case
Why
of
it get,
yes.
sir, why it get half?
What I have told you, I have got these formulas from derivation. Is it got half? You need to derive these relations. Okay, you have to find these the derivations using. So the derivations are there in your SL Aurora book. Okay, you can get it. How you get it means how this formula arrives. I am not telling you how this formula has arrived. I am telling you how to remember the formula. Okay, so simply dividing it by 2 means this is I'm not telling you how this formula you have got. I'm not telling you. I'm telling you I already have these formulas. I have these formulas with me already by deriving them. Okay, now I want to remember them. So how to remember? This is what I am telling. How to learn them. I'm not telling you how to derive them. Okay, that derivation I have told you earlier using the calculus method and then using the parallel and perpendicular axis theorems, we can derive these formulas. So we have already done the derivation of these formulas. I already have these formulas. Okay, so I'm not taking the derivation here. Got it? I'm just telling you, you have this table given with you. This table is now you need to remember this table. Okay, this is so simple. Just focus on this part. How? Yes.
Which derivation, sir?
Derivation is there in my lecture number. You can see my previous videos. Okay, the derivation I have told you how to derive these formulas. So you can see previous lectures. There will be derivations. Okay, in my previous videos. Okay, first thing is from my videos. Yes, see my previous videos where I have taught moment of inertia and how to derive. I have written in the video, the heading is theorem of perpendicular axis and theorem of parallel axis. So there I have derived these relations. Okay, see the previous videos and then SL Aurora book. You can do the derivations. Okay, now let us see how to remember these formulas. So I told you that see the concept, we know that the mass, if the mass is distributed near to the axis, okay, then the inertia, so this r will be lesser, so inertia will be lesser. So here this is mr square, if this case of ring, and here this area inside is filled, so it becomes a disk. So in the disk it is reduced by half, so it is easier to rotate the disk, okay, as compared to ring. Now it is further and the same, so it is divided by 2, and here also this is this mr square. If I rotate it with diameter, you can see that here I have this means the mass is near to the axis. Now this mass has reached near to the axis, so that is why the inertia is reduced by half. So if we rotate it by diameter here, again it will be reduced by half. So it is half already, so half of half is 1/4. So that's how we got I've got these formulas. Now the same formula for this and I've told you that this is the general formula mr square, so it is not difficult to remember. This is for suppose a particle with mass m. This particle belongs to extended body. Okay, this is not sole particle. This particle P belongs to some extended body, and this is axis of rotation. So this is your extended body, and one of the particle I have taken. So what is the inertia of moment of inertia of that particle? That is mr square. So that's the general formula also for a particle. Okay, so see, same is the formula here, mr square if the axis is C. So same the case with the ring, means moving it along the perpendicular to the plane passing through the center. So here also it is, you can see that it is the same case, this hollow cylinder, and this was sort of a hollow disc, so that we call hollow disc as ring. So same is the case here, mr square, and here also it is mr square. And if it becomes solid, like here it became solid, so after it became solid, again it will be reduced by. So I hope that you have remembered this, how to remember these formulas. Okay, now this is ml square by 12. This we need to remember, we have no option. So this is something like mr square, but this is ml square and divided by 12 for the rod. And here also you have no choice, mr square, yes you have, but this is 2 by 5th, okay, for this cylinder. Okay, so students, just how to remember the formulas. Now we have the next topic, that is dynamics of the rotational motion. So now students, what we need to do in this topic? In this topic we are going to derive these formulas. Derivation. We are going to derive these formulas. Kinetic energy we already derived, okay, so we are not deriving it again, but we are deriving the formula. Torque we already know, moment of inertia we already know, so we will be deriving basically the formula for power, formula for angular momentum, so and this formula for torque, this we already derived. Tau is equals to means this we already know by definition of the torque, but so primarily we will be deriving these three formulas. First of all we will derive this formula of power, and then we'll be deriving the formula for this torque, tau is equals to I alpha, and then we'll be deriving this formula, L is equals to I omega. So this is what we are going to do. So students, for this we need to look at the figure 7.3 and 7.33 and 7.34. Students, I have got the result of camp also that you gave last year. So Bhumika, those who have got the merit certificates, certificates of merit, Veena, Sakshi, you have got a very good rank. Veena, you also, Mansi, you also. Karthik, I think you have not given the camp exam, right? Last year. So Veena, Sakshi and Mansi, you three have given the exam and you have got very good rank at state level and at national level. Congratulations to all three of you, and congratulations to other students also, because they are also your teammates. So all three of you should never skip my class, it's very important. Okay, somehow students, let us look at this figure. I'm unable to arrange them properly, but still, see this figure. Suppose I have my particle P, just discussed particle P rotating about this and told you that particle P is part of the extant body. So this is our extant body and this particle P, and this is where we have taken the origin. Okay, and origin, so means this is my xy plane. So suppose my particle P can be anywhere in this whole body. So what you are going to take, if you are going to take this particle over here, so this axis will be if we have particle, suppose P here, so the axis that we will be taking will be parallel to the x and y axis. So this I can take this x dash and y dash. So similarly, I have taken this axis. This is x dash, y dash. Got it? This axis, this axis. Okay, and so this is a diagram of this axis, x dash, y dash. So this diagram I have chosen part of this diagram from here to here. Is this clear to everyone? Now this was your so what's another difference? Here you have taken it written it as theta naught, but here I am writing it as theta, and this part I am writing as a theta naught. Okay, so this part I am writing as a theta naught. So this part I am writing as a theta, and this part I am writing as theta naught. So the particle was at position P1 here at an angle theta, and then it was displaced by angle d theta to position P1 dash. Is this clear to everyone, students, this figure? How we have got this figure? Next thing is that this figure is your all these variables that you see, they are in the plane of your notebook. They're in the plane of notebook. If you have drawn this figure in your notebook or in your book, so this is the plane of book. Okay, this is the plane of your book. Is this clear? Next thing is that we consider only those forces that lie in the plane perpendicular to the axis. Okay, and the forces which are parallel to the axis, they will even give torque that will even move the axis. Okay, so we are not going to consider them. So see, this is not going to be anywhere near in the lecture today, but this is the very important assumption that we take. Like we take the assumption that acceleration is constant. Okay, so we will be dealing with them, but you need to understand that yes, we have studied this concept that we need to consider only those forces which lie in the plane perpendicular to the axis. So we will be considering only the force which are lie in the plane of this plane of your notebook or plane of your book. We are only going to consider those forces. Is this clear? Next thing is that we need to consider only those components of position vectors which are perpendicular to the axis. So perpendicular to the axis means that only those position vector. So which ones are perpendicular to the axis? So this plane is perpendicular to the axis. This is the axis of rotation, and this plane, this x dash y dash plane, this plane is perpendicular to axis, right? This plane is perpendicular to the axis of rotation, right? Axis of rotation is z. So the forces that you are going to take, the position vectors that you are going to take, they are all supposed to be in xy plane. That is the plane of this book. Okay, so these are the two assumptions that you need to take. So in this figure we have the work done by the force F1. So this is the force. So this is the same figure, if you remember that for the torque, when we were calculating the torque, so the force F1 was in this direction. That's the same figure, and this was your vector R1 vector. This is F1 vector. So this is the same here. This distance I have taken as R1 from here to here. Okay, is this okay, students? And this let us draw this figure again. So this is very important to understand this figure. So we have this P1. What is P1? So see, theory is written in your book clearly, everything. So the particle at P1. So we have a particle at P1. At position P1. So this is where the story starts, and it describes a circular path of radius R1. So this R1 is your radius with the center. So this C is your center. So this is your complete, this circular path, and this CP1 is your radius, that is R1. So in time delta t, the point moves to position from P1 to P1 dash, and the displacement of the particle on the arc means the displacement of the position straight means this is point P1, this is point P1, and this is point P1 dash. So what will be the displacement? Displacement is directly initial position to final position, and that displacement is this displacement is ds1. Okay, so that's ds1. So that's given here. This distance is pp1 distance is ds1. And what is this ds1? See here, this d theta is so small that this arc and this there's no difference between this arc and this straight line. So we can treat ds1. This is another important assumption that we take in physics. If delta theta is very, very small, if delta theta is tending to 0, then we take ds1 as arc, and we take ds1 as line also. So they are the same if delta theta is very, very small. So we know that this arc is equals to radius into angle. So here we have this ds1. I can write ds1 as r1 d theta, isn't it? This ds1 is equals to radius into theta. So arc is equal to radius into theta. And see, this you have done when you are doing chapter number 2, parallax, right? And direction, what will the direction of ds1? What is the direction of ds1? So this is the direction of ds1. This is tangential, right? This is the direction of whose direction is this? This is the direction of ds1. Okay, this is the direction of displacement, right? Which is tangential to the circular path, because this d theta tending to 0 means it is actually a point, but this figure is enlarged. Okay, so that is why you see this much. Actually it's a point, means you are reaching to a point. This p1 you are bring them as near as possible. Okay, so here what is angular displacement? This d theta is your angular displacement, very very small. So don't go by this figure, because we have enlarged so that you are able to understand the concept. So now what is the work done by the force? This is the force that is applied on this particle which is at p1. So the force is given by dw1 is equals to f1. So force is f dot s, so force into displacement. And what is so find the dot product. So magnitude of f1 into magnitude of ds1 into cos. So what's the angle between them? f1 and ds1. So this is f1 and this is your ds1. Okay, right? So what's the angle between them? We have taken the angle between them as phi1. So this is cos phi1. Now put the value of ds1, which is f1 into r1 d theta, right? So this is the value of s1 we have put. Now what is the value of cos phi1? See, this angle is if you extend this radius, so this radius, radial, this vector, radial vector, and this is tangential vector. So tangential and radius, so this is a radial vector. Okay, so the angle between the force and radial vector is taken as alpha 1. So this is the angle between, so we need it for the torque, right? So this is your direction of r1. So when we're writing the formula, torque is equals to, so that will be r1 into f1, r1 cross f1, and that will the magnitude will be writing as its magnitude as r1 f1 and sine of alpha 1. Is it okay, students? So now what is phi 1? So the whole phi 1 plus alpha 1 is equal to 90 degree. So I can write this cos as cos phi 1 as 90 minus alpha 1. Yes, can I write it like this or not? Okay, so dw1 is equals to f1 r1 d theta into cos 90 minus theta is sine theta, so that's sine alpha 1. So that's the last line of page 169 of your NCERT. Now what is your tau 1? So we write it as tau 1. So tau 1 we have just calculated, that is equals to r1 f1 sine alpha 1. So let us take this equation as equation number 1 and this equation as equation number 2. Okay, now put this value of equation 2 over here. This is f1 r1 sine theta 1, right? So that's so what this dw becomes. So put second in first. So what do you get? dw1 is equals to tau 1 into d theta. Okay, now students, see why we are writing 1 1 1. It might be irritating you, because see we are considering only one of the particle. We can take it as I also instead of 1. Okay, but why I am taking 1? Because I am starting with particle 1 and then particle 2 and then particle 3 and so on. So that is why I have taken first particle. Now if there are, and for all the variables, so if there are F1, F2, not one force, but if there are a lot of forces, etc., acting on the body, then work done by all of them can be added, right? Because work done, it's a scalar quantity, then work done by all these forces can be added. Okay, so work done by all of them can be added. So what is work done? That is net force, right? Net force into displacement. So net force, how will be writing net force now? So now rewriting this equation again. So if now see I have removed 1 from here. Okay, so now this dw is for the body, for the extended body. Okay, so that was for one of the first particle 1 1 1, and now I have removed 1 here. So net work done by all of them, so that will be so tau 1 plus tau 2 and so on into d theta. So instead of tau, so now I have taken the impact of all the forces acting on this particle. So not still the body, but still means still it's I'm taking it as so this was due to the force F1 only. So students, this F1, so why I was taking the particle, and due to the force F1, so this F1 was for the force. Okay, so all these 1 1 1, why I have taken this 1 1 1, this 1 1 1, these 1 were due to the force F1. Okay, so now force F2, so all of them will become 2 2 2. For F3, all of them will become 3 3 3. So for not particle 1, but for force F1 I have taken. So this 1 that I am writing is due to the force. So now I have taken all the forces now, so this 1 will be removed. So net work done on the by all the forces on this particle is dw, and I can add all the forces, and that's dw is equals to tau into d theta. So this is the work done by all the forces. So let us assume it equation number 3. Now differentiating this equation both sides with respect to t, we get dw by dt is equals to, so tau is the constant, and this is d theta by dt. So what do you get here, students? What is dw by dt? That is your instantaneous power, right? So I can rewrite this equation as power is equals to tau into d theta by dt is angular velocity. So that's the formula you have got. So you got the formula of work, you have got the formula of power. Okay, so that you can write as equation number 4. Now we have work energy theorem. So we have work energy theorem, that is work done is equals to change in kinetic energy. So and means we can write it as dW is equals to dk, and again differentiating both sides with respect to t. So dW by dt is equals to dk by dt. Now put the value of dW from equation 3, that is tau d theta by dt you will get. And what is k? K is half mv square for linear motion, and here half into moment of inertia into omega square. So you have simply put dW is equals to t, and I is equals to, k is equals to half I omega square. And now this has become omega, so tau into omega is equals to, and here half is constant, I is also constant. And what is now d by dt of omega square? So first of all, omega square, that is 2 omega. Now here if it was t square, so d by dt of t square, the answer will only be 2t, that's over. But here it is the variable is omega, so we have to derivate this omega with respect to t. So student, this is the difference. So remember, this is the law of differentiation. Okay, so here I get this 2 omega into d omega by dt, and omega will be cancelled here, and this 2 will also be cancelled. So what do you get here? You get tau is equals to I into, what is d omega by dt? dv by dt, that is your acceleration. So here it is angular acceleration, that is alpha. So that's your new equation. So this is your equation number 5. So this is all about, this is equation 7.43 in your book. So we have completed this topic, students, and you have very simple example 7.15. Try it all by yourself today, or if you want me, shall I do it for you, or you will try it all by yourself first?
Try, sir.
Okay. Okay, you will try yourself, right? So can you try it just if you have a couple of minutes, or you will try it later? See, just it's very simple. There's a code of negligible mass. Just read it out. You have couple of minutes. Come on. So this is your flywheel here. Radius is r, mass is 20 kg, radius is equals to 20 centimeter. So of course that is equals to 0.2 meter. And you have a pull of 25 Newton. There is a cord which is wounded on this wheel, right? So you have horizontal axis, okay? So this is your axis of rotation and this is horizontal. And this wheel is, you can see it is vertical and this is horizontal axis. So perpendicular to the plane over here is your axis of rotation. You have to find alpha here. So you know that tau has two formulas, right? Tau is equals to, one is F is equals to ma. So remember students, we have two formulas like here. So if you have tried it out, that's good. Otherwise you can look here also. So F is equal to ma, so tau is equals to I alpha. One formula we got from here, and the second formula we get from the definition, that is tau is equals to R cross F, and tau is equals to, the magnitude will be R perpendicular into F. So that is R perpendicular into F. So you have F over here, you have I. So what is the I? We just discussed it today. So it's the flywheel. So if it was a ring, and then it was mi square, but it's a flywheel. So this is all. So moment of inertia of the flywheel, it's all solid. So its moment of inertia is mr square by 2. So moment of inertia is mr square by 2 into alpha. You have to find R perpendicular. So that's your radius. So you can write it as R also, and then the force. Force is your 25 newtons. Okay. So simply now you can cancel out this R. One R will be cancelled out. So now put the values. 20 kg into radius is 0.2 meters divided by 2. So what alpha will become? So it's better if we write it algebraically first. So alpha is equals to 2f upon mr, right? So that is 2 into 25 upon m is your 20 kg and radius is equal to 0.2. So this comes out to be 50 upon 20 into 0.2. So this point will remove and this 10 will come here. So hope you have done it, students. So this 10 will cancel out, this 50, so 2, it's 25. So what's wrong? What's wrong here? Yes, have you got the answer, any of you? What is the
Sir, you are doing right.
I'm doing right, but the answer is supposed to be angular acceleration is 12.5.
Sir, cancel 25 with 2.
Radians, yes, 25.2 radians per second square. Okay,
Yes, sir.
so that's correct. Now let us quickly do B part. What is the work done in unwinding this? So dw is equals to, yes, tell me the formula, come on quick. What is dw is equals to tau into d theta? Yes. So what is the work done in winding? 2 meters. So that's equals to, and but here we can use this formula also, because 2 meter is the displacement, means length. So F into ds. Yes. So force is 25 newton, and we have pulled 2 meters of so force is 25 newton, and we have pulled 2 meters of length. So that comes out to be, so the work done comes out to be 50 joules. Okay, now C part. Final, how much is the kinetic energy of the wheel at this point? So See, for kinetic energy, we need kinetic energy is equals to half moment of inertia into omega square. So we need to find the final kinetic energy. So to find the final kinetic energy, we need to use the formula. We need this. So omega square, v square is equals to u square plus 2a s. Okay, and this is 0 here. So it is at rest. So and what is theta here? So theta is the angular displacement. How much will be the angular displacement? Theta is equals to 2 meters is the distance moved, and means upon 2 meter, that's the radius of the wheel. So total length wound is 2 meters, and the radius is only 2 meters. So you can see that it will be 10 radians, right? So that's your theta. So putting this value of theta over here, so you will get omega square is equals to, this is 0, so this is 2 into alpha is 12.5, we have just calculated, into theta is 10. So this comes out to be 250. So this because units are here square, so here also those units will be in square. So radians square per second square. Now this is now we can simply put, that is why I have not done the under root, because I need to find the value of omega square. So put this value of omega square over here. So what do you get? K is equals to half into I is 0.4 mr square. Yes, so you can find I, that is mr square by 2. So what is I equals to mr square by 2, and that's equals to 20 is the mass and 0.2 is the radius divided by 2, and this comes out to be 0.4 kilogram meter square. So that's your I. So put this value of I over here, that's 0.4 into 250. So this comes out to be 50 joules. So you can clearly, students, see that this work done was 50 joules, and kinetic energy is also 50 joules. So work energy theorem is again proved here. So work done is equals to change in kinetic energy. So here initial kinetic energy was 0. So that is why work done is equals to, so whole work done is changed into kinetic energy. That's all for, so there is no loss of energy due to friction. So thank you so much, students, for being with me. I will upload the video. If anything is left, you can complete your work with the video. Okay, thank you so much.
Thank you.